So, essentially you will find that the statement that if there are no vertical forces acting on the beam, there will not be any vertical reaction force developed is not always true. It depends upon whether the beam is statically determinate or indeterminate. In indeterminate system there can be a vertical reaction force developed even though there is no vertical force acting on a beam. Okay. So, that is what I want to emphasize here. Similarly, you can work out the condition for different end conditions, say as a fixed beam or fixed guided support and things like that. Okay. But in all these cases we are estimating a P critical load as a single load which occurs suddenly and the deformation was such that either the deformation is 0 or it shows a large deformation at a particular value of stress. As I demonstrated in the last lecture, through a scale the deformation is continuously bending along the lateral direction when I apply a load. So, this does not seem to reflect the reality. So, let us now analyze a case where it reflects the reality. The reality is the column is not ideal. What I mean by that is the column is not prismatic or straight or the load is not applied to the center of the cross section exactly. You know that in an experiment it is not possible to always apply a load exactly through a particular point. If you apply a load through a particular point, it is a point load and it has to have some distribution, some length to distribute itself to a uniformly distributed load. So, that is also not advisable. So, when you distribute a load over an area, it is not possible for you to ensure that the distribution is uniform over that entire area. Okay. So, there will be minor eccentricities in the load. Okay. Now, let us analyze what happens when there is a load applied slightly eccentric to the CG of the cross section. Okay. I will go back to a simply supported beam, simply supported column with an eccentrically applied load P. I have this eccentricity E coming in there. E might be a small value, but it has an eccentricity E. Okay. Now, I go through the same procedure, the column deforms into some shape like this, I cut it here, I draw the free body diagram, there is a load P acting at a eccentricity of E from the neutral axis, okay, to the axis of the beam. I have P here. Now, the moment this P in, again I assume that the vertical deflection is absolute value of delta y. Okay. Now, then I have a moment mz coming in here which will be a clockwise moment to counter the anti-clockwise moment produced by the axial force. Okay. So, that will be now mz moment is given by P into E plus absolute value of delta y. Okay. P into absolute value of delta y. Okay. Now, delta y is negative downward. So, this will be P into E minus delta y, because delta y is negative in a downward deflection. I am assuming still my coordinate system to be x, y and z. Okay. Now, this should be equal to, from the beam bending problem, E times I z z d square delta y by dx square. Okay. Now, solving this differential equation as before, I can write that as d square delta y by dx square plus k square delta y equal to k square E, where k is square root of P by E times I z z. Okay. Now, the solution for this equation is delta y is C1 cos kx plus C2 sin kx plus E. Okay. Now, the boundary conditions are delta y at x equal to 0 has to be 0 and delta y at x equal to L has to be 0. Okay. This tells me that C1 plus E has to be 0 and this tells me that C1 cos k L plus C2 sin k L plus E has to be equal to 0. Okay. From here I get C1 to be minus E, okay. Then I get C2 to be cos k L minus 1 into E divided by sin k L. Okay. Now, having found C1, now I can simplify C2 further as E times cos k L minus 1 can be written as minus 2 times sin square k L by 2, okay, and this is 2 times sin k L by 2 into cos k L by 2, okay, and this becomes minus E times tan k L by 2, okay. This becomes 2 times tan k L by 2. Having found C1 and C2, delta y now substituting for this becomes E times 1 minus cos k x minus tan k L by 2 into sin k x. Okay. Now, let us proceed further. We have found delta y to be E times 1 minus cos k x minus tan k L by 2 into sin k x. Here we did not find anywhere we were able to apply the boundary conditions without requiring P to take a particular critical value. That is the first observation. Okay. The next observation is we want to find delta y max. Okay. To find delta y max, I have to write d delta y by dx has to be equal to 0. Okay. So, this will imply that k times sin k x minus tan k L by 2 into k times cos k x must be equal to 0. Okay. So, this will imply that tan k x must be equal to tan k L by 2. This implies that x must be equal to L by 2. Okay. So, d delta y by dx equal to 0 gives me the location of the delta y max. So, delta y max occurs at x equal to L by 2 and this is delta y max then is E times 1 minus cos k L by 2 minus tan k L by 2 to sin k L by 2. This I can simplify further as E times 1 minus cos square k L by 2 plus sin square k L by 2 divided by cos k L by 2. Okay. This gives me C times 1 minus secant k L by 2 because cos square theta plus sin square theta is 1. Okay. So, I got delta y max as E times 1 minus cos k L by 2. Okay. Here again now I am interested in plotting how does this function delta y max vary with respect to p. Okay. Now, I have delta y max to be given by eccentricity times 1 minus secant square root of p by E I z z into L by 2. Okay. Now, you know that secant is a function which varies from 1 to infinity. Okay. So, secant tends to infinity when secant square root of p by E times I z z to L by 2 tends to infinity when square root of p by e I z z into L by 2 tends to 2n plus 1 pi by 2 n equal to 0, 1, 2 and so on. Okay. Now, the p critical minimum then is pi square E I z z by L square corresponding to n equal to 0, okay, when n is 0. Okay. Now, for this p critical load is same as what we found from the ideal column buckling or the Euler buckling load. Okay. So, if I were to plot delta y max, if I were to plot delta y max as a function of p, then what will happen is as p tends to p critical, this is p critical minimum, this delta y max will vary from when p is 0 it is E, okay, and p is 0 and this is 0, this is E, and it will go asymptotically to that p critical value. Okay. So, this is like what the scale did. When I applied a load, for small load there was some eccentricity and the eccentricity grew or the lateral deflection grew as the load was applied more and more. Okay. So, this is how it behaves for delta y max as a p critical. Now, let us find what is the maximum stress that this section can see or this metal can see, this body can see. Okay. So, we found delta y max, we found delta y, I have to find the stress now. Okay. The stress is given by sigma xx is due to bending plus sigma xx due to the axial force that is applied. Bending stress is given by minus mz by izz into y minus y naught from the bending equation, and this is given by p by area of cross section A. Okay. Now, I know mz from our previous expression, I know mz from our expression here, that is given by p minus delta y, e minus delta y, p into e minus delta y. Okay. So, and I found delta y to be this, and I found delta y to be this. So, e minus delta y would be so I will get this as minus p into e into cos kx plus tan kl by 2 into sin kx, okay, to sin kx into y minus y naught by a into r square, where r is a radius of gyration as before, plus p by a. Here also I should have add the bracket there because axis is negative, okay, into p by a. Okay. So, now this I can write it as p by a into e by r square into, I want sigma xx max, the maximum stress will occur at the extreme fiber. So, I will have y extreme fiber in compression y max in compression into cos kx plus tan kl by 2 into sin kx plus 1. where yc max is the location of compression fiber, location of extreme compression fiber from neutral axis. Okay. Now, I know that the maximum deflection occurs at L by 2. So, if I were to maximize this, if I were to find d sigma axis max by dx equal to 0, to find the maximum location along the z direction, it will again be L by 2, and hence sigma xx max both in x and y would be p by a e yc max by r square into same expression as before, this will be secant kl by 2, kl by 2 plus 1. Okay. Now, this k also contains p. So, I want to write everything in terms of, let me define sigma xx apparent as p by a, the actual stress that is applied. Okay. So, this will be sigma xx apparent into e yc max by r square into secant sigma xx or secant square root of p by e a into L by r, where r is the radius of gyration and a is the area of the cross section, plus identity. This will can be written as sigma xx apparent into e yc max by r square into secant sigma xx apparent by e square root into L by r, okay, to L by r plus 1. Okay. Now, so I have this to be limited to sigma y uniaxial, since the state of stress is uniaxial, and if the yield stress is sigma y uniaxial, this will be limited to sigma y uniaxial. This will be sigma xx apparent into e yc max divided by r square into secant square root of sigma xx apparent by e into L by r plus 1. Okay. Now, I am interested in plotting sigma xx apparent versus the slenderness ratio lambda L by r. Now, you find that this secant term will tend to infinity as sigma apparent tends to p sigma critical, the Euler buckling load. Okay. You find that this term tends to infinity when sigma xx apparent is equal to sigma critical that we found before, which will be nothing but E times pi square E times L by r d whole square. Okay. So, if the sigma critical curve were to be like this as a function of slenderness ratio, this is sigma critical curve, okay, and this is sigma y, if this is sigma y uniaxial line, okay, when the load is, when the slenderness ratio is close to 0, the slenderness ratio is close to 0, secant will be close to 1, okay, then this curves will look something like this. Do something like that, where this is with increasing eccentricity E for a given section. E increases along this direction, eccentricity of the cross section. Okay. So, if the eccentricity of this is say 1 mm, eccentricity of this might be 0.5 mm equal to E. Okay. So, as the eccentricity increases, the curve will tend down from the critical load. Okay. So, this is how the apparent stress will vary as a function of slenderness ratio. Okay. Okay. So, this reflects the realistic behavior of the column, wherein you have the lateral deflection also depending upon the load, and you have the stress going to the yield stress value of the uniaxial yield stress value depending upon what the eccentricity and what the slenderness ratio is. Okay. And by the way, this is called as the secant formula. Okay. Now, there are other variations by which you can generate realistic behavior. The other possibility is, instead of applying an eccentric load, it can be just like what we did for the equilibrium. You can give a disturbance wherein you have a simply supported beam, wherein you can say I applied a lateral load W like this. Okay. Then also you can redo the analysis, get the critical load for this beam to be the same as pi square E by lambda square, and you can show that all that what we did now also holds. I will not be doing that in this course. Okay. The other point to note is, once you have an eccentricity, the direction in which the column bends would be the direction in which the eccentricity of the load is. Okay. So, if I add a load acting with which is eccentrically displaced upwards, then this column will deform only down. On the other hand, if I add this load eccentric downwards, this column would deform something like that. Okay. So, the eccentricity governs the direction of the displacement of the column and is no longer a random event. Okay. But whether it deforms in along y axis or whether it deforms along the z axis depends again upon the moment of inertia along y or z, whichever is the least, it will deform perpendicular to the least moment of inertia direction. Okay. So, with this we conclude our discussions on stability induced failure. We saw how an ideal column will behave and how to get the critical load for an ideal column, and then we saw a case wherein we had a real column behavior exhibited by a simply supported column subject to an axial load. Okay. How we could capture all the realistic behavior by assuming the load is acting somewhat eccentrically to the center of the cross section. Okay. Now, in the next remaining lecture we will see an example problem wherein we will work out an example problem involving the failure theories as well as the stability induced failure. We will work out an truss problem wherein we will analyze what is the maximum load a truss can take, incorporating both the failure theories and the stability condition, and then we will work out an example problem involving failure theories and the inflation of an annular cylinder problem. Okay. Thank you.